So let's start a breathing sphere. I have a sphere which is perfectly round, and coordinate I'm measuring from the center of sphere that I call R is a measure of the distance from the center of sphere. Now, assuming this one is vibrating with magnitude U0 and the frequency of omega. And this will vibrate and radiate sound. And suppose the radius of this sphere is A. Okay. Before we start to see this radiation problem theoretically, let's close our eyes and then suppose we are fluid particle somewhere over here, and suppose you are fluid particle somewhere over there. And suppose you are seeing the fluid particle nearby yourself. And the wave if each fluid particle experience depends on wavelengths. Okay, as well as frequency. And we remember that the radiation depends on frequency as well as wavelengths, because the everything propagating is related with a dispersion relationship that simply say K equal to omega over C. Okay. And what about the radiator size? If radiator size is small compared with wavelengths, that means I want to see the size of a radiator with respect to wavelengths. And that is pretty much related with Ka. If Ka is small, that means radiator size is small compared with wavelengths. Okay? Radiator size is small compared with wavelengths. In this case, radiator size is A. For example, the wavelength is this amount. The characteristics of radiating sound would be quite different compared with the case when Ka is large. When Ka is large, then the radiator size is large compared with the wavelengths. That means this breathing sphere radiates wavelengths like this. Okay, in both, in two cases would be quite different. And obvious things that those characteristics has to be measured with respect to Ka, as we saw before. Okay? So let us see how this kind of things can come out by studying this radiation in analytic way. Okay, let's invite the velocity potential phi. That would be depending on r as well as time. And say this will have some arbitrary amplitude. And obviously it will decay 1 over r and then exponential minus j omega t minus kr. How do I know it depends on 1 over r? Okay, there are several ways to understand. that will depend on 1 over r. First, theoretically, this velocity potential function satisfy this governing equation. You can derive this from the general governing equation and this Laplacian has very complicated form in terms of theta, phi, and r. And we do know that there's no dependency with respect to theta and phi. Then we will come up with the this governing equation. And this is interesting because that means r phi will be plane wave, right? So I can write this is a times exponential minus j omega t minus k r. Therefore, I can write this. So the result comes from the solution of this governing equation. And we know that this governing equation is holds for every case. And I just convert this governing equation to this rather simple case, which is in this case the theta and the phi depend. There's no theta and phi dependence. Okay? You see, it is amazing that in all the days, the acoustician always start with this very rather unusual looking simple case, and then they found the physics, and then they expand to understand rather complicated case. So we have this, and taking a derivative with respect to space, I can get a velocity d phi dr. So let's take a derivative of this solution with respect to r. This will give me a 1 over r square and minus, I'm taking derivative with respect to r over 1 over r. As you know, this will give me minus 1 over r square. And then I have exponential minus j. I will use theta, and theta is simply the abbreviation of j omega t minus kr. And then second term, I have a and 1 over r. And then I have to take a derivative of this argument with respect to r. This will give us what? Minus j minus k, that is plus jk, right? And then I have exponential minus j theta. Okay, that is the velocity in r direction at any point. So let's rearrange this expression in rather compact form, and I can say this is a, and I have minus 1 over r square over here, and I have plus r and jk. Okay, is it correct? Okay, and then I have exponential minus j omega t minus kr. Okay, that is velocity. Okay, then what would be the velocity at r equals a? then this formula gives me the velocity at r equal a has to be a minus 1 over a square plus jk over a, and I have exponential minus j omega t minus k a. That is the velocity. And that velocity has to be same with this, because I assume that breathing sphere will vibrate with magnitude u0 with frequency of omega. So what I can do here, u0 exponential minus j omega t has to be equal to a minus 1 over a square plus jk over a exponential plus jka and exponential minus j omega t. So this relation determines the assumed amplitude A. Therefore, we can write the amplitude A has to be, this is common, has to be u0 divided by minus 1 over a square plus jk over a, and I have exponential minus jka. That has to be the amplitude of velocity potential. Okay, that is we are getting a formula that certainly start to exhibit the physics behind of it. Because it has A and K. Oh, we got Ka over there. But it's not very interesting because it just to say the exponential jk is the real part. What is the real part? Real part is Ka, imaginary part is, but it still does not, I mean, it has some meaning, but it does not really exciting at the moment. So let's change this form so that we can see, or we can at least feel the physics. Okay, then I can change this like that. Okay, if I multiply a square, right, in both sides, then I will get minus 1 plus jka, and I have a square and then exponential minus jka. That is the amplitude of A. Okay, that means the velocity potential would be the phi RT has to be equal to u0 minus 1 plus jka, a square, and that is A, and 1 over r exponential minus j theta. Okay, that is velocity potential. Because we have velocity potential, we can obtain pressure and the velocity. Okay, what would be then velocity in r direction? Okay, let's try to do it. I hope everybody is following me. Everybody is following me. Okay, I mean, this is the least derivation you have to do the acoustics. Okay. So what is the dphi dr? Okay, that will give me, I have u0a square, and I have minus 1 plus jka. Taking a derivative with respect to r will give me minus 1 over r square. And I have exponential j theta over here. And I will take a derivative with respect to theta, that is omega t minus kr. So this will give me what? I take derivative with respect to r, then I have j minus will give me plus jk. Okay, this is what I got, right? Additional term. Additional term exponential minus jk. Okay, now this is velocity in r direction. So if I write velocity, here? Okay, right. Plus jk r. I think that is correct. Okay. So velocity, therefore velocity in r direction can be written as u0 a square minus 1 plus jka, and I have minus 1 over r square plus jk r, and then I have exponential minus jka, okay, and then I have exponential minus j omega t minus kr. Okay, is it correct? Okay, now, what is then pressure? What is pressure? Okay, pressure at point R with respect to time is equal to minus rho 0 dphi dt. And we know the function phi, that is, as we saw over there. So I will write again u0 a square minus 1 plus jka. And then taking a derivative with respect to time, I have rho 0 over here. And taking a derivative with respect to time will give me minus j omega. Okay? And then I have exponential minus j omega t minus k r. And I have exponential minus jka. Right? Okay? Okay, now, so I have pressure and I have velocity, and it looks very interesting. Let's first look at the pressure term. Okay, pressure term.